This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
This week we have Brian Bailey from the University of Illinois at Urbana-Champaign, and he has done work in a variety of areas, including interaction for creativity, which is interesting. Some of you may know there's a conference being held in June in Washington called Cognition and Creativity. Is that the?
Creativity and Cognition.
Creativity and Cognition.
It's still the same one.
Right. And if you're interested in the topic, that'd be something to take a look at. But the work he'll be describing here is looking at interaction and the relationship of attention and focus. Brian.
Great. Thank you, Terry. So today I'm going to talk about a topic that I think is incredibly important in the modern workplace, and that's interruption. There are, of course, many sources of interruption in the workplace. My work focuses on those interruptions that are caused by notifications in the interface. Notifications are not inherently bad. If used judiciously, designed appropriately, they can be a very effective awareness technique that users do appreciate. Our mission as a community should not be to design them away. Our mission should be to design them effectively. My work addresses a very key challenge in that design space, looking at when notifications can be delivered such that they have a reduced cost of interruption to the user's ongoing task. So today I'm going to talk about results from a range of projects that we pursued over the past 5 years, looking at systematic methods for picking these moments throughout a task sequence, looking at what type of empirical benefit one could expect from doing so, a bit of theoretical interpretation about why it works, and then how do we take the positive results we've had from our lab studies and move them into practice. An example of the situation that I'm interested in is when a user is engaged in a task, could be searching the web, writing a research paper, or programming a complex algorithm. And there's a system or application that has information it wants to relate to the user. Could be update of collaborator activity, could be a communication request, it could be a sudden change in the weather, whatever it is that the user might desire. Now there's many challenges in this space to get this just right. One challenge is knowing when notifications are appropriate technique. Another challenge is coming up with a visual standard that we could utilize in the interface, because we don't have one today. Now, I just take those as assumptions that somebody's going to address that. My work does not currently look at those two challenges. My work looks at a third and what I think equally important challenge of when would be an appropriate moment for notifications to be delivered to the end user such that it would have a reduced cost of the ensuing interruption. I think that's a very important challenge for a couple of reasons. One is that results from a recent field study have shown that users receive, on average, 7 notifications per hour of their workday. And I'm not going to say that all of those are appropriate, but users do receive many, and I don't see this trend discontinuing anytime. So anything that we could do that, that would have a positive impact would be beneficial. Second, though I'm interested in this particular domain, it's not exclusive to this situation. So in-vehicle systems with the driver, ubiquitous computing spaces also share similar characteristics. So we hope that the solutions that we develop in this space might have broader implications in these other areas as well. I want to make a case that notifications are, in fact, good. One of the key advantages of notifications in the interface is that they preclude the user from having to visually sample or poll a secondary display or application. And almost all the empirical research shows that behavior occurs when notifications aren't there. And if we do them correctly, users often appreciate notifications in the interface. So a quote from a recent field study shows this point, where the user says, notifications are useful because they prevent me from having to go to my application, in this case Outlook, as often. Okay? So I don't think that our mission should be to design them away. Our mission should be to design them more effectively, because they come with a cost. Work that I've done, work that Mary Sterinsky has done at MSR, and a variety of other people have shown that notifications in an interface do have a fairly substantial cost in terms of task completion time, error rates, and feelings of frustration, annoyance, and anxiety, or what's often referred to as negative effects. So what we'd like to be able to do is understand how we maintain utility of the notification, but mitigate cost. McFarlane calls this one of the most challenging problems in HCI today. And I think this is why, if you look back through the last 5 years of the SIGCHI proceedings, you see a lot of very talented people working on this particular problem. Now, we need to look at system architectures, I think, that try to maintain or achieve this desired balance. But I've always felt that the answer to this problem is going to come from understanding human architecture. Okay? Many years ago, cognitive theorists were already thinking about this particular problem. Miata and Norman, in particular, were doing so. And they argued very eloquently in their article, which is now widely cited in the Interruption literature, that if you can find moments of lower mental processing effort or mental workload, those would be the moments where you'd have reduced cost. They further speculated that those moments would occur at breakpoints in a task. Let me give you a very simple example of what breakpoints would be. So if we can go to this overhead. So they're showing me. Oh, you're all seeing. Okay. I was looking down at the monitor. Okay. So what their theory essentially argued is that if we have, say, a Word document and you can do a couple of edits to that, okay, just do a standard hierarchical decomposition of that particular task. So your root goal is to do the revision. Your sub-goals are to do the first edit followed by the second. And then in each one of those sub-goals, you're going to redo in the review and the actual edit, okay, followed by the second step. What their theory basically argues is that if you notify the person at each of the arrow points, so in between the subtasks, then that would be a moment of lower disruption for the user, as opposed to doing it during any one of the subtasks. Now that fits very nicely with theories of attention, which would argue that a person would have more attentional resources to allocate to the interrupting task and would require fewer resources to get back onto the primary task. There's also a number of practical advantages of using breakpoints. One is that almost all goal-directed tasks have breakpoints. And second, as I'll show later, we can detect them. My work takes this theoretical construct as input into my research process. And so what is the empirical benefit, if any, of actually doing this? Are all breakpoints the same, or are some better than others? How do we detect them in practice and make this work for the end user? That's what my research tries to address. Now, this is in context of a much broader picture of work that's going on with notification management. There are two main areas of research here. One's called mediated techniques, another is called negotiated techniques. Mediated techniques are where you sense a variety of cues about the task sequence, the environment, the social engagement, and so on, and try to make reasonable decisions about when would be appropriate moments to interrupt. And a variety of people have been working on this. Eric Horvitz from Microsoft, James Fogarty, who's now at Washington, have done some outstanding work in this area. My work makes a contribution to this area of mediated techniques by allowing those techniques to leverage the structure of the user's tasks. That's important for two reasons. One is there's an empirical benefit of doing so. And second, it gives a link back into the theoretical constructs that allow us to interpret and explain the results that we get. And I think that's actually been missing from the research to date. Now, the other technique are called negotiated techniques, and these are embodied by what's often called peripheral displays. They allow the user to choose when and how often to check for new or updated information. These work very well when the updates are of lower frequency or urgency, but when you have the expectation of information that has higher utility, you'll get this polling behavior. And again, almost all the empirical research backs that up. The way that peripheral displays try to address that is rendering attentional cues. Those are notifications as well. So I would like to see some convergence in these two spaces, where perhaps mediated techniques could identify more opportune moments to render attentional cues so the user can more readily switch their attention. This is actually a good breakpoint in my talk, if there's any clarifications. Otherwise, I'm going to move into some of the empirical work that I'll start with. So any clarification questions so far? Oh, that is an example of a peripheral display. This is the scope system. that was done at MSR a few years back. Okay, so this gives you a nice persistent visualization of recent notifications that you have received as a user. Okay. Anything else?
Oh, have people tried to combine this before?
They have not, and I would love to see them try to do so. We repel each other as opposed to embracing each other. And so I think that the solution in the future has to be more about convergence between the two threads of research.
I had a question about how an understanding of attentional processes informs this model. You said that there are points at which cognitive effort declines naturally. I mean, don't people maybe need that as a kind of breakpoint to kind of rest? Or, I mean, does the...
Maybe. We don't know yet. And what we do know is that people do take periodic mental exhales, and I'll show some results to actually verify that. But the jury is out on whether or not you actually need those moments as some kind of natural inclination for the task. But what I'll show you is that I have some empirical results that show if we do that, we actually can get a positive benefit. Now, if we do it in practice over a long period of time, I guess there's a question about whether or not that benefit is retained, or if people want those mental exhales as part of their natural sequence. But we'll see. Good question. Okay. So the first thing I wanted to do is test that basic underlying construct. Does deferring notifications actually have a positive benefit for the user? It's actually, at that time, it was untested. Okay, so I wanted to put together a very simple controlled experiment to test this basic theoretical construct. What we did is we had the user perform 3 instances of primary task categories, and we had 6 categories. We did things like reading, adding, image comprehension, and so on. And during those 3 task instances, we had the user perform 2 peripheral tasks. In one condition, they would do the peripheral tasks during the primary tasks, and in another condition, we had them do it between. Okay? Now, there are 2 important properties of the experiment. One is that we controlled for task workload. That's important because a lot of the work today doesn't do that. Okay, in the one group you have, say, do the primary task, and in the other case you do primary plus the peripheral. You have to be careful because the results then could be attributed to the differences in the task workload, not to the particular intervention that you were using. So we controlled for task workload. And second, it's really simple. Because if we can't show a positive result with this experiment, it's really doubtful that we're going to be able to do it in practice. So let's see what we got. Okay. When those peripheral tasks were delivered between the primary tasks, we found a 47% less anxiety. And the way that we measured anxiety was with the state trait anxiety inventory form. It's a paper-based questionnaire. You do it in a pre-post format. You subtract the pre from the post measure, and then you compare it between the groups. Okay? So when those peripheral tasks were delivered between the primary tasks, users in that between group reported a 47% less anxiety. So that's a good result. They reported 36% less annoyance.
So can you give us a quick flavor, Brian, of what primary and secondary tasks
Oh,
look like?
so the primary tasks were along the top row, secondary tasks were along the bottom row.
You can't read those.
Oh, you can't read those, sorry.
Small print.
Okay, so in this case, I'll just go through this example, Scott. This is image manipulation. And so I had like a little tournament bracket. And they would ask you questions such as, what was the score in the final game? How many points did they win by? Who played? And things like that. And then in the peripheral tasks, you would do a stock update. So I'd give you a little scenario that was trying to be as realistic as possible. And I'd ask you to make a decision. And then the other one, it was a news update where you'd have to read it and then answer a question to make sure that you actually had done that. So that was basically what we did. And each of the 3 along the top were similar but not the same, because you can't ask people the exact same set of questions. Sure. Okay, so that's what we did. And we had 6 different categories of those in the top row. Okay, error rates were low overall, but we had a 50% fewer errors. Yes.
It's not by Clippy, so annoying.
Clippy might be annoying for other reasons other than just inappropriate interruption, perhaps. Yes. Yes. So there has to be a desirability of what that thing is going to offer, right? So the assumption here is that the information that's being conveyed through the notifications is in fact desirable by the end user. Thank you. And we had no negative impact on task time. Okay. So overall, these are pretty positive results that strongly suggest that if you pick the moments that you send notifications to the user, you can in fact have a positive outcome. Okay. So that's good. Yet, you should be concerned is that it was too controlled and that the moments that I picked were obvious, right? I set up the sequence of tasks so that the coarse-grained breakpoints were obvious. What happens when you have a more complex task? How do you do it then? And almost all of the work in the interruptions literature uses random or periodic moments. If you get a positive outcome, it's very difficult to make that repeatable. So what I wanted to do is try to identify a repeatable method for making predictions about better and worse moments in a task sequence. So after reviewing quite a bit of the psychology literature, we came upon one promising technique known as event perception theory. This was done by Zach some years ago, and it builds upon work that Newton and others did prior to that. What this theory says is that though the incoming sensory stimuli seem continuous to us, it is in fact being segmented into a two-level hierarchy, what they call coarse and fine units of action. And there's breakpoints in between each of those units of action. Now, what's really fascinating about this body of work, it shows that if multiple people are viewing the same sequence, you tend to pick out the same breakpoints. If you combine that outcome with the theories that Miata and Norman put forth earlier, then we might have a repeatable method. So I wanted to test it. We used 3 tasks. We had a media summarization task, we had a web search task, and a document editing task. And we recorded ourselves doing those tasks. Okay? I then had 30 users review each of those task sequences. And the first time they reviewed it, I asked them to write down a brief linguistic explanation every time that they perceived a change in action that was both meaningful and natural. Okay? The first time they did it, it was the smallest units of action. And then the second time, it was the coarsest units of action. Merge them together, and the predicted best points would be those that have the highest frequency count that people agree upon, and the worst points would be the subtasks where there's most disagreement between the fine unit breakpoints. Okay? Same basic evaluation paradigm that we used. The user had performed in the same tasks that were originally recorded, but we now had a different set of users. We would watch them perform the task via a VNC connection, and when they hit those points that were predicted best and worst, we would basically give a pop-up. Okay? It's modal, because we had to control for the timing, and they would perform that peripheral task. What we measured was subjective workload using the NASA TLX, frustration, as well as social attribution, thinking about the system that was interrupting as a social actor. So we want to know how frustrating it was to receive those notifications. Here's what we found. The best moments relative to the worst, and this is across tasks, no one category of tasks explains all the results. Reduced frustration by 33%, improved social attribution by 30%, and it reduced time pressure, which is one of the 5 dimensions on the TLX, by 45. Best relative to random, similar outcomes. So this is good, okay, a fairly positive outcome, but what I think is the most important contribution of this work is that we have a repeatable method that can be applied for predicting the better and the worst moments, and we got favorable outcomes for doing so. Okay?
What's the social attribution in this case?
A level of respect that the system had for you. And I would ask you to rate that on a scale of 1 to 7.
Treating the system as an actor.
Exactly. Got it. That's exactly right. So why does it work? Well, the assumption is that people have these reductions in mental processing effort as they move through breakpoints. Is that true? I wanted to find out. So the next project, we wanted to link a physiological measure of mental processing effort with ongoing task execution. And we wanted to overlay those 2 data sources and look at what happens at the breakpoints relative to other parts of the task. So for the task, we used a route planning task, a document editing task, and an email classification task. So for route planning, what you would do, if I can do this without advancing my slide, you would take your cursor and you would roll it over one of the segments. You'd get a pop-up of distance and fare information, commit it to memory, and then enter it into one of the rows of the table. Repeat that for every segment of the route, then do that whole process again for the second one. Email classification, you would read the subject descriptor, and then you would look at what of the 4 folders that should actually be dropped into. And you repeat that a number of times. The tasks were very carefully controlled because everybody needed to do the same sequence. We needed to have well-structured tasks that we had very kind of salient boundaries. And they couldn't be too long, about 5 minutes was sufficient. What we'll find is we generate a ton of data when we do this. Now, for the physiological measure, we chose to use pupil dilation. This is a measure that really dates back to the mid to late 1800s. It's been systematically studied since the 1960s. And what it says is that if I engage the user in a cognitive stimulus, the pupil will dilate slightly. And this is a very reliable effect, okay, across tasks and people. It also has a number of nice properties. It's immediate, it's continuous, and it's low latency. So about 300 to 500 milliseconds after the onset of stimulus, the pupil will ever so slightly begin to dilate. And the amount of dilation is correlated with the amount of mental processing effort. This can be explained nicely, I think, in terms of the analysis that we did by looking at a new tool that we developed to help with this. It turns out that Excel wasn't optimal for analyzing this type of data. So this uses an interactive overview plus detail visualization. If you just focus on the bottom pane, you can get the sense of what we're doing. The top part of that is our task model, extended for time. So the root node extends for the duration of the task, and then they get smaller as you go down into the model further. The wiggly line is, we can just think of that as the mental processing effort. And what we wanted to do is look at what happens as the user moves through a breakpoint relative to other parts of the task. Now, there's a lot of interest in our field about using workload as a new metric to evaluate complex interfaces. It's a very exciting area of research. But one of the things we lack are good tools. So I also think that this tool, which is downloadable off our website, can help move that forward by making it easier to do analysis of this type of data. So that should give you a sense of what we're trying to do for the analysis. Terry, you have a quick question?
Really good question. You say that tool downloadable, what does it require in terms of hardware?
It runs in Java, so...
No, in terms of watching the...
Oh, okay, so we support the iLink 2. I should mention this, that the data format that we support is the iLink 2, which is a head-mounted eye tracker. It's done by, I think, SR Systems, if I have the name right. It has a very high spatial accuracy and very good temporal resolution. So we get a stamp of the pupil every 4 milliseconds. So we support that data format, but you can plug in via our architecture parsers for other types of formats as well. Thank you. Okay, so here's what we found. First, we found that workload tends to fluctuate throughout the execution of a task. Okay, that's not necessarily surprising, but I still think this is an important result. Because what it says is that we don't grab a big pool of resources and maintain that throughout. We're adaptively allocating them. That means that timing of notifications is important. The second finding that we had is that as a user moves through their task execution, they experience reductions in mental processing effort at some, but not all of the breakpoints. Those reductions tend to be larger at those breakpoints that are higher in the model, and they tend to be lower at points lower in the model. Now, I'm using the term tend because there certainly are cases that the upper level breakpoints had very small reductions, and some of the lower level breakpoints had larger reductions. The difference to me is really thinking about the difference between doing a formulaic application of GOMS, where all the breakpoints look uniform, and doing something where you're actually measuring workload, where you find those points that are meaningful to the person. Okay? If you want the precise ordering, then you have to do the alignment. And trust me, you don't want to do this. This took about 18 months to do the analysis of this type of data. Very complex. Rather, you could use our results to provide an empirically based set of heuristics. So just assume that the cost of interruption is lower at the high level boundaries and not quite as good for the second and so on until you reach about the third. Because after the third, you don't really find anything. So about 3 levels deep is all that really makes sense in this case. But yet, that seems to be, in my opinion, a little bit naive, because you lose all of the structural characteristics of the task model itself. So what I wanted to do in our next project is look at, could we leverage the characteristics of the task model to make better predictions about which breakpoints were better and which ones were worse? We had 3 tasks. We used the same 2 as last time, the route planning and document editing, and we threw in a third, which was a video editing task. We built models for them to about 3 to 5 levels deep. We don't go further than that because we want to allow for some variability in the execution sequence. And about 3 to 5 levels of the sub-goal structure achieves that balance. What we looked at is we really just kind of dug through the research literature, and we looked at what other people had predicted might be predictors of cost. So things like what percent of the task do you have complete? What percent of the parent subtask do you have complete? How much carryover was there between the individual subtasks? What level in the model are you? Things of that nature. Okay? So we had users perform the tasks, and we'd send them notifications at a random sampling of the breakpoints. We collected what I consider to be a very true empirical cost of interruption known as resumption lag. This is how long it takes them to disengage from the secondary task and get back up to speed on the primary task. Okay, and that's usually on the order of milliseconds and seconds. We applied a series of machine learning techniques to look at which of those predictors would be predictive of the resumption lag values that we had collected. Guess what we found? Level in the model, the amount of mental carryover from one subtask to the next, and the difficulty of the next subtask were the three predictive factors. It's mental processing effort. That's what's really interesting about this result. So it's the current and prospective allocation of attentional resources that were predictive. Now, the correlation coefficient was relatively modest. 0.26 is significant, but not so meaningful. Okay? So what we wanted to do was trade precision for accuracy. So don't try to predict the actual numeric value. Predict a class that contains a range of values. To do that, we combined visualization techniques with k-means cluster analysis, and we came to the conclusion that about 3 cost classes were right. For the lack of a better term, low, medium, and high cost. Now, what's fascinating about that outcome is it's consistent with what Fogarty found in his Chi 2005 work on also there's 3 essentially cost classes. As systems builders, what this tells us is that our systems are not going to be able to reason at a finer level of detail than 3 cost classes in practice. So we learned a mapping using a neural network-based approach. What we do is we go into our model, and for every breakpoint is we code the level, the carryover, and the difficulty of the next subtask. We use some well-known techniques for doing that. I borrowed some techniques that Chris Wickens had used in his prior performance modeling work on how to come up with the values. It's fairly subjective, but it's the best that we have available to us. And we try to make predictions about the cost class. Run a standard 10-fold cross-validation, and we want to look at the results that we get. So here's a confusion matrix. Along the top, you have the predicted values. And along the vertical column, we have the actual values. And so the diagonals are where we got it right. Other locations are where we did not. The overall accuracy was about 63%, which is better than chance and always picking the most common one. And the most egregious error was relatively low. So this is where I test the audience to see if you're paying attention. Which one is the most egregious error? The lower left, actually. So where we predict low, but in fact it's high, would be the most egregious error. So that was only 5%, so that's good. Now we wanted to go one step further, and we wanted to test the generalizability of our model. Would it work for different tasks? So we did 2 additional tasks. We did a collage generation task and a freeform design task. We do the same basic methodology. Okay, so we build the models. We pick a random sampling of the breakpoints, and as users engage in the tasks, we send the notifications to them. We use our neural network that we had developed, and we make predictions about each one of the different breakpoints. Okay, and we go through and we code it just like we did before. And we compare the actual to the predicted values. So same type of confusion matrix here. And again, the diagonals are where we got it right, other places where we got it wrong. Same overall qualitative distribution of the results. The overall accuracy was about 53%, which was better than chance and always picking the most common one. The most egregious error is a little bit higher in this case, but overall I think still pretty good. How does one test if this is good? As a final metric, what I wanted to do is I wanted to group the actual resumption lag values by their predicted cost classes. Now, using predicted cost class is very important because it includes the errors that the system had made. And what we found is running a basic ANOVA on the data showed that all of the pairwise differences were significant, and I would argue also meaningful. If a system would defer a notification from a high cost class breakpoint to a lower cost breakpoint, you save the user on average about 1.4 seconds for resumption lag. That's a fantastic result in my opinion for a couple of reasons. One, as far as I know, this is one of the first interventions that actually shows a positive benefit for the user. Okay? The second is that it shows us what we can expect in practice. Okay, so this is a single notification. So if we did this for many notifications for many people, it should, over time, have a nice impact on productivity. Now, I didn't test other things like frustration and so on, but perhaps we'd also get favorable outcomes on those dimensions as well.
Hey, Brian.
Yeah.
You can defer this one if you want. One study that I like a lot is Mary Cherwinski's work showing that if you have more screen real estate, where you can basically spatially array. I mean, because the canonical interruption thing is an email message comes
That's
in.
right.
Whenever I think interruption, I replace that with new email comes in, or IM or something like that. And as opposed to having it pop up on top, if it pops up to the side, one might theorize that we only glance over there only when we only at these boundaries.
Mm-hmm.
Is there any data on whether that's actually the case? Like,
That is actually the case. There's lots of qualitative and quantitative data that shows that when people negotiate their own attention, they
Yeah.
almost always self-negotiate a breakpoint. That's a fairly robust finding.
yeah.
Now, the technique of basically mediating in space is an interesting one, and I think that goes to what I said earlier in my talk about wanting to have a standard technique that we use. And there's a couple of papers in CHI 2007 that I'm looking forward to looking at on how you do that kind of mapping. I think that's very important. It doesn't say that we don't need the timing manipulation, which I think that we do.
Yep.
I think we're going to need convergence on those two avenues of research.
Both temporal and spatial.
Absolutely, absolutely.
Yep.
I wouldn't necessarily say spatial. I would say a visual standard. Whatever that might be color, might be size, might be topography, but it also might be spatial.
Well, because I mean, the simple one would be if I'm writing a paper and an email pops up right in the middle of the paper at a random time. That's
Right.
obviously obnoxious. Whereas if it pops up not overlapping my word window, then that enables me to self-negotiate.
It can be. So I would direct you and others that are interested to what Chris Wickens did with his sieve model, where the effort that it takes to actually notice the peripheral information is predictive of the attention allocation. And so you have to be a little bit careful, because what you're saying for the less important things is going to require more effort to look at them. Maybe that's the right way to do it, I'm not sure. But it's an interesting thing to think about for sure. Okay? Now, we have the model, and what we want to look at now is how do we start automating this process that we've shown to be effective in some of our experimental studies in practice. So we began exploring some of the systems design challenges for doing this. Let me just take you through the diagram that you see on the right as a way to explain the vision that we have for the system. We would have a set of task descriptions, which are just machine parsable formats of the types of models I've talked about earlier. And I'll show you a language description for actually describing those. We would leverage existing, or we'd have to build our own, instrumentation in applications that give us the application level events. And what we want to do is look at the incoming user event stream and compare that against the task descriptions that have been developed, and essentially follow the user through their tasks so we know when they hit the breakpoints. When an application wants to gain the user's attention, it would send a request to our system along with a time frame. Is it the next 5 minutes, the next 10 seconds, what have you? And I assume that time frame would be mapped from, say, the relevancy and the urgency of the notification. And then we try to find the most opportune moment in that time frame to deliver the notification. There are two main components to our system. One is the task description language, and the other is the task monitor. Now, when you design these types of task description languages, one of the things you want is the ability to have hierarchy. You have to name the events in the event stream, obviously, and you need to describe the variability that's common in how different people perform the same task. So we drew upon XML. It has nice hierarchical properties. You can obviously name the event, and we used regular expressions for describing the variability. So just a simple example of scheduling a series of appointments in Outlook would look something like you see on the right-hand side, where your main task is to schedule appointments. Then you can do one or more of the following subtask of adding the appointment. You have to do the set of events in order, and then the next two may or may not occur, but if they do, they can be in any order. That gives you the sense of the types of things you'd have to describe using our language. You don't have to do detailed comms models. You can have any level of detail that you want. If you just want to do application switches, you could do that. But this is about what I would expect in practice. Now for the task monitor, what we try to do is compare the incoming events to the allowable events described by the description itself. We use an algorithm that's based on the use of position placeholders. Okay, so we just basically put a pointer into your task description. We look at your event stream and try to figure out when we advance it. The basic challenges here are when you instantiate the descriptions, when you advance the placeholder, and when you discard it. The basic contribution we made in the system is that we support multitasking behavior. So we can have multiple descriptions open at any given time. Our algorithms are based upon computing what we call the next set of allowable events. If you want the details of that, I would just refer you to the journal article. I just want to reflect a bit on the system and talk about the doability of this in practice. I think this is doable for a number of reasons. One is that descriptions can be at any level of detail. You only have to design them once, and they can be reused. And if you focused on the higher frequency or safety critical tasks, you have the most benefit for the least investment. This is most suitable when it's desirable to have this precise representation of the task itself. But admittedly, I agree that not all situations are like that. So as a final project, we pose the following question. Can we detect those points that we're most interested in, which are the breakpoints in a task, with no representation of the task itself? The way that we approached this particular problem is we revisited that work that Zach's had done that built on work by Knudsen. And recall that this is a particular theory that says though the experience of the incoming sensory stimuli is continuous, it's in fact being segmented into a two-level hierarchy at least. And that we have the breakpoints between those units of action. Multiple people who view that same sequence tend to agree on where the breakpoints are. Well, if we could identify the cues that people are picking up on, then it might be possible to map that ongoing execution to the detection of the breakpoints. So we wanted to test that basic idea. The way we did it is we collected some field data. This is no longer controlled data that we had. This is actual field data. We collected 3 different domains. We had a graphic design domain, document editing, as well as programming. We had 2 people who I had no affiliation with. Okay, these are actual professionals in every category, who the next time that they're going to be engaged in one of those tasks, we would ask them to run our software, which would basically collect their screen interaction and log all of the events that you could possibly think of with the keyboard and the mouse. Okay? So about an hour and a half, and then when they're done, we'd come and we'd collect the data. We had 2 sets of data for every category. Okay, so 2 from graphic design, 2 from programming, 2 from document editing. We then had a group of 24 observers come into the lab, and they would annotate where they perceived the breakpoints occurring in that data. We built a tool to help with the analysis. And what the observer would do is every time they perceived a breakpoint, they would decide whether it would be a coarse, medium, or fine, and they would write in a linguistic explanation as to why they thought it was a breakpoint. Now, the earlier work showed that there's only coarse and fine, but all the empirical data suggests 3. So we went with 3. We tested 4, but we didn't find that people could perceive more than 3 different types of breakpoints. Okay, that's how we came to coarse, medium, and fine. Now, the choice of observers was also very important because the observers do not share the same internal understanding of the task as the users themselves. And so they would have the same information available to them as a future statistical model would as well. And so if we could find it with observers in terms of agreement, then we could probably do it with the model as well. So let me start with just characterizing the breakpoints. We found, as you might suspect, the fewest coarse and the most fine, and medium in between. 756 for coarse, 1,050 for medium, and 1,268 for fine across the tasks. Now, interestingly, this wasn't always true. If you look at row P2 and row DE1, you find almost the opposite effect. Okay? And looking back at the interaction videos explains why. Interaction is extremely fragmented. Okay, we're very schizophrenic in how we do tasks. 4 to 5 minute bursts are pretty much about it. So we'd see things such as a person's engaged in writing a line of code, they'd switch, they'd check the news, they would check an online media player, they would then do their email, then they'd come back and do it all over again. Okay, so that kind of explains some of the differences, I think, in the data. Now, we also analyzed the linguistic explanations to try to get a sense of what were breakpoints. For coarse breakpoints, people tended to say that switches to unrelated activities would be coarse-grained breakpoints. Mediums would be switches in the source object, so a different document, a different graphic design file, a different source code file. And fines would be switches between actions on the content, so italicizing a set of text, boldfacing it, things of that nature. It's interesting what wasn't a breakpoint. Finishing a sentence, finishing a line of code, those were never identified as breakpoints. And it's really about, people just don't work like that. It was never, I write in a sentence, I never write a line of code, I'm just jumping all over the place. And so those types of solutions would probably be pretty naive in practice. Okay, you have to have a deeper understanding of breakpoints and how to identify them. Okay.
Evaluating video again?
So we would say every time that you perceive a transition between a unit of execution that you believe is both meaningful and natural, that's the exact same instructions that all the previous work has given. Okay? So in other words, we didn't instruct them on what to look for.
Did you give them the course medium and fine?
We did give them coarse, medium, and fine. We would say whichever of those three types you believe it to be, go ahead and mark it down.
Would they go back and say, oh, that wasn't the course?
So they had the option to do that. We did not observe that happening very often. Okay, thank you. We also were interested in the temporal distances between breakpoints. These are on the order of seconds and minutes. So for example, if you just completed a fine breakpoint, it would be about 7 minutes until the next course, about 3 minutes until the next medium, and about 2 minutes until the next fine. This is really important because we are going to do deferred breakpoint policies in practice. This is about what we could expect for how long things need to be deferred until you reach the next breakpoint. I believe this is doable. Okay, I believe that seconds and minutes is doable in practice. Then we had to build the models. So the first challenge was to figure out how we wanted to delineate the models themselves. So we have one global model that does everything. Should you have a series of models for every type of breakpoint and application? We went with one course because those were independent of any particular application. And then we had one per application and doing both medium and fine. Okay, so we had a total of 4. We looked at a broad range of candidate features. So all the things have been talked about in prior work, an analysis of linguistic explanations and our own common sense of what might be valuable. And we had to filter the breakpoints. There's some standard techniques that we apply. We get rid of about 50 to 75% of the breakpoints in doing that. What's fascinating, though, is how you find the agreement in the breakpoints themselves. Okay, because we use that then for the ground truth. We also include into that set a random sampling of places where there were no breakpoint to allow for differentiation. We learned the models then using standard neural network techniques. You just plug it into WEC and it spits out the model for you. It's really nice. Here's what we found. Now, I'm going to go ahead and just collapse the data for purposes of brevity. If you're interested in the more precise numbers, I have those with me. For the observers, what we found is that our models could detect 87% of the course breakpoints. It could detect 76% of the medium and fines for graphic design, 69 for medium and fine in the document editing, and 76 for programming. So overall, pretty good. Now, we also did one final metric. We had the users themselves come back in and annotate their own breakpoints because they share that they have their own internal understanding of the task. We want to look at how good the models, based on the observers, would do for the users themselves. What we found is that we could detect 77% of the course, 68 and 86%, and this is then for each of the 2 users for graphic design, 56 and 73 for document editing, 50 and 14, which is the anomaly that we have to further investigate for programming. So overall, it's a little bit less, but you might expect that since it's the users and not the observers. The question is this good, right? And I would argue that this is good because you do not need 100% detection accuracy to make this work in practice. You just have to get enough of the breakpoints that will allow things to be deferred until those times. And I believe that the numbers that we're showing is good enough. Now, of course, you want to probably have more robust models. You add in additional features, you have more training cases, you have more data, and I think that we can actually boost the numbers slightly.
You were putting it in places where the error, like programmer 1 was like, well, that wasn't the breakpoint, but then you thought I had a breakpoint here, and I,
well, so
you just interrupted my workflow.
So if I understand your question correctly, I would say that the error rates would be the opposite of the numbers that I'm showing. So we'd have 23% errors for course, 32 for graphic design for the 1 user, and so on. Now the question is, how much of those
of programmer 2's breakpoints?
Right, absolutely. Now the question is, how much is there overlap between the user and the observer? there's actually a fair degree of agreement between those two data sets. And so users weren't picking randomly different breakpoints than what the observers have picked. Now, there are differences, but there's enough overlap that we still get pretty good results. Thank you. So in conclusion, what we've shown is that deferring notifications until people reach breakpoints in practice, or until they reach breakpoints, can reduce cost along completion time, along error rates, and feelings of negative effect. We've shown a little bit about why that's the case, and the fact that mental load tends to exhibit transitory decreases as people move through breakpoints in a task execution sequence. We have a method for predicting the cost of interruption at different breakpoints in a hierarchical model. And we've shown how to detect breakpoints without knowledge of the structure of the task itself. And we've also looked at some systems development challenges of how do you automate this in practice. And what we've been doing recently is we've been building these statistical models for Word, Visio, and Microsoft Studio. And the value of the models is that we can throw out those representations of the tasks that we had in the system, but we can use the other scaffolding that's already available. And so the idea is that the next time you're engaged in writing a paragraph or working on a complex algorithm and a notification is generated, it's going to wait until you finish that current cognitive chunk before it displays. And I think that's going to be a very valuable thing for the end user. A number of future challenges, since I do have a little bit of time. I've been focused really on cost. And we haven't done much in the community, not just me, but in the community overall, about how do you dynamically compute the utility of the notification. And I assumed in my system that we would map that utility value onto a time frame, okay? But I've kind of punted on how we do that. And so I'm looking forward to doing some work, either me or others, on how you compute that dynamically. We haven't done enough on how we map utility onto the visual technique, as Scott had pointed out earlier. Should we do differences in color? Should we put them in different spatial regions? Or so on. That's something that we haven't done, and we need to do it. We need to study deployed systems in practice. And it's not just to look at if we get an overall benefit, but how do people adapt? You know, people are always very clever about how they interact with intelligent systems. Do they game the system? For example, do they do something that they know the system's going to say, oh, that's a breakpoint. Let me show you what you have. Or is it going to be something different? Okay? So I think that's going to be a very interesting avenue to study. And I think we can study some of these principles in other domains. So one of the projects that we have ongoing now is looking at attention in the automobile. I'm also doing some work on coordination of communication via mobile devices. So taking this notion of attention and looking at it not just in the desktop, but other domains as well. I'd like just to conclude by acknowledging some very hardworking students, as well as some people that had given us some money to pursue the research. Thank you.
Another question. I realize this isn't what you were measuring with your experiment, so I'm just curious what you think about, which is the other side, which is the nature of the interruption. So if I get an RSS feed versus an email versus an IM, for example, there's a different sense of how bad it will be if I just ignore it for a while.
Right.
Are you looking at those kinds of measures?
We haven't done that, and I think we need to do more of that type of work. So I mean, what I wanted to do, and I think this would be a nice way to get at an answer to your question, but essentially record the different notifications that people receive over time and sit down with the user and talk about why this might have been valuable or why it's not, and see if we can come up with some heuristics and guide designers on here's what's appropriate to send via notification and here's what is not. Maybe we need to make things more configurable. So what types of options could we give to the end user to say more of these and less of these? That might be a valuable way to address that as well.
About switching between applications, and you also talked a little bit about task carryover. One of the things that's happening a lot in certain spaces is that you need to make decisions getting information from a variety of sources. And so application switching happens in the middle of a task, and it doesn't really, in my mind, sort of make it a break point. It's a bringing together point. How do you think your model is going to handle this, or what do you have in mind to deal with that?
So great question. We perceived exactly that when we looked at the data. And remember what I said about course breakpoints. I didn't say it was switches in applications. I said it was switches between unrelated activities. Very easy for people to identify, and what we'd find is that the observers would make very rapid judgments on is this related or not. And detecting that, of course, is very hard for a system because you have to do some form of content analysis. Now, what we did in our models is we did something a little bit clever, but not overly challenging. We grouped things in different categories. So online news, online media players, things of that nature. And we looked for switches between that. I would call that very low-hanging fruit. So we could have a pretty good estimate that if you switch from programming to the online media player, that was a switch in unrelated activity, and would therefore justify a course breakpoint detection. So that's how we addressed it. But we talked about in this paper about how you might want to bring in some more type of content analysis to make comparisons. So thank you.
A question about lag, which is, say I switch to the news. By the time you realize it's time to interrupt me, I'm busy reading the news already.
Yeah, that's right. So what we don't know yet is what is the cognitive duration of a breakpoint. And we always say exactly what you said. Well, once we detect it, then we can render the notification. But we don't know if you've already gotten up to speed on that task. And I would actually say that's also something we wrote about in our recent paper about understanding what is the cognitive duration of a breakpoint. It would be very fundamental to understanding how well this would work in practice. I mean, the other thing you do is just try it and see if it works.
You would sometimes detect the end of the breakpoint.
We detect the end. Yeah. So are breakpoints instantaneous or do they have duration? I don't know. I would argue a bit they have duration. And we did a little bit of analysis when we did the eye tracking study. We did a little bit of analysis on the duration. And if I remember correctly, the ones at the top level are on the order of a second to a second and a half, and the lower level ones were a few hundred milliseconds. So it does seem to suggest there's a duration. Now, you could try to come back into our system and say, well, let's detect the beginning and the end. I don't know how to do that. I'm not sure if it would be effective, but it's something that we could try. Right now, we treat it as an instantaneous moment.
Actually, I would say that in some cases, breakpoints are the moment that the user is actually most sensitive. For example, you're writing a document and you are looking for a reference in your own document. So you switch from writing to, let's say, searching. But at that point, you are actually keeping in mind several things that you don't want to interrupt because it will break the continuity of what it is that you're doing. And now you're working mentally rather than the mechanical of typing.
Yeah, so I would completely agree with you. And the one thing I should say is that nowhere in my talk would I say I'm going to get it always right. And we're going to get it wrong sometimes. I think the question is, can we be right often enough that it works in practice? And can we combine this with Scott's suggestion to do a nice redesign of the visual technique? So even if we get it wrong, the visual technique is still minimally intrusive. That would also be very important.
I think Uri's example of what he mentioned was an application switch, which is different than it sounds like what you would call a break.
That's right.
So if I understand your work correctly, that example would not be a breakpoint.
It could be a medium breakpoint.
Okay, it could be a medium breakpoint.
So what we find is that switches between applications that are related would often be referred to as mediums. Now it brings up the question of how do you do the right policies? And so we're giving a range of policies one could use. Defer to any breakpoint, defer only to the next fine, only to the next medium, only to the next course. If it turns out that when we do some of the controlled studies that only to the next course is the thing that you have to do, well then we'll go with that.
Why not just use that to determine when you actually have lower cognitive load, and assume that the user has an adequately high resolution webcam that can track their eye?
No, that's a wonderful question. Now for pupil dilation, it probably wouldn't work because there's too much change in the ambient luminance that one has in a work environment. But more broadly, I think that might work. It might give you a small improvement, but here's the key: you lose all of the structural characteristics of the task. And what we found was really that's almost the most important. So even if I know that the workload is low, I might still be engaged in typing. If you combine that, though, with the structural characteristics of the task, you can find the pauses in the execution sequences themselves. And that is what I believe is the most important part of the work. So I wouldn't recommend using a physiological-only approach. If you combine that with the structural characteristics, then sure. But think about what we've been doing. What we've been doing is trying to essentially bypass the need for the physiological measure by using reasonable heuristics about identifying which breakpoints are better and which ones are worse.
So,
Scott,
go ahead.
Go ahead and I'll go back.
It seems like some of this would involve some level of what's often traditionally been called user modeling would be handy here. And a lot of the work on model-based user interfaces had two goals. One was to be able to dynamically generate different kinds of user interfaces based on device constraints or user models, something like that. And a lot of them a lot of that work was motivated by, as opposed to specifying widget kind of things, you would specify in a manner that seems more felicitous with your XML notation. Have you thought about, you've done a lot of work on design tools also, have you thought about how one would wire in that kind of task notation into Dreamweaver, Flash, Visual Studio, that kind of thing?
Well, if you want to use the work that Bonnie and John has done, you actually have some extensions, say, to Flash that you can demonstrate the task. And if you just went through and demonstrated the most common ones, it would actually spit out something reasonable that would fit with our language. That's one way you could do it. But it still takes effort. And different people are very unique in the way they perform tasks. And so it's really hard to describe all the variability. And so that's why we try to do something that didn't have the representation of the task. Now, coming back to your modeling question a bit, should we have one set of global models that everybody shares, or should we build user-specific models? And the only way that you want to build user-specific models is you get a nice improvement in detection accuracy. I mean, it's going to be really small. The investment that it takes to build the models per user, it just doesn't make sense. And so we're actually doing that study right now. We're looking at the differences between having a global set of models and user-specific models to see what kind of improvement you can get for detection accuracy. And if it's not enough, we're going to push for going with the more global models.
Using the pupil dilation as effectively a detector for breakpoint. And as I understand it, James Fogarty's work originally was about trying to figure out what the set of sensors that you would need in order to determine interruptibility would be. And then you've kind of followed on that by instrumenting the software environment or the operating system environment to do detectors. But if you looked at doing, well, what else could you get by having more sensors that could detect various aspects, and also just within the operating system environment, I mean, what are the ones, did you look at what are the most predictive breakpoints?
Okay, so his early work looked at sensors that you put in the environment. His more recent work actually looked at how you put sensors in the software. Okay, now when you put sensors in the environment, it's very important to look at which ones are most predictive, because there's a cost associated with doing so. Putting the sensors in the software is basically free. And so for us, it didn't really make sense to try to say, well, this is the most predictive, this is the least predictive. We just wanted to know more in a binary sense, what's predictive, what's not.
It seems to me that if you put those in the environment, you have another level above your course. Which is like the person gets up, goes away, it's exactly.
Oh, absolutely.
Like you don't have in your experiments because they're done in single sessions.
So that's absolutely what we want to do. So one of the things that we want to do is expand the range of sensors that we have. Okay, so one of the things I'd like to do is look at spatial features, as whether or not that is actually boost the prediction accuracy of breakpoints. There's also just work breakpoints. Maybe that's the fourth breakpoint that you have at a more macro level, but I get up and leave and I come back and I engage in my HCI type tasks. That might be a nice breakpoint too, to just have a nice summarization window of the notifications that you've recently received. That would also be something that we'd like to do. And if we had more resources and time, we'd absolutely be willing to do that.
What about, you had your slide with the timings between different classes of breakpoints. What about using that as help improve the prediction?
Yeah, absolutely. And so if you look at, say, the priors, if I know it's been, say, 100 seconds since your last find breakpoint, and on average is at 110, there should be a way to get that into the model. I need somebody who knows more about machine learning than I do to figure out exactly how to make that work, but absolutely that can be used as input to that machine learning algorithm.
Learning, my own biases there, admittedly, but neural nets are certainly not the best.
Okay.
They're the least, and the point is, once you understand your problem, that's the first one you toss out.
Okay.
To go on the other end of the spectrum, your problem reminded me of basically a secretary helping her boss do his task, or Mythical Man Month, a surgeon being helped by his team. Humans, at least some humans, are very good at figuring out when to interrupt you. Also, some are obviously very bad, but anyway, to say the least. But have you talked to anybody who's very good at that, for instance? You have misses and false alarms here.
Sure. So let me separate your two questions into two parts. First, the reason that we use neural networks is because it doesn't assume independence of the factors. And so like naive Bayes actually does. Okay. Well, we'd be happy to use better models. And if we had better models,
the results will always be worst of all.
Well, that's good, because I think we got pretty good results with the models that we did use. And so we had better models, we should get better results. Yeah. So I'd be happy with that. Point me to the right literature on that, and I'd be happy to look into it.
Brian Flax here wrote the thesis here, Mike Flynn, and he was actually the architect of the cell processor, but anyway.
Okay, I'll do that. I was gonna say,
That's not necessarily the best, but that's the one I'm familiar with. And he has some comparison among different techniques, and among the things, the neural nets were the worst.
So we have not done the social engagement aspect of the work. We're trying to do that, but more in the domain of mobile devices. And there we are working with people to understand. We just completed a diary study where we asked people every time that they made or received a call to report what type of context either they considered or wished that the other person had considered before they called them. And then the goal is to try to understand what cues we might put into awareness display, how we might visualize them to help coordination of communication via mobile devices. And we just published that. If you're interested, I'd be happy to point you.
What if the boss doesn't know, the secretary knows how she could help him?
Well, it's
I mean,
interesting.
the user is the least qualified in some sense.
Yeah, I would agree. Nobody has studied adequately yet the issue of social relationship in this process. And so I would argue that my boss could care less if I'm busy. If they want to actually interrupt me, they're going to. But if it's somebody who's in my inner social circle, they have more of a investment into not interrupting me when I don't want to be. That's actually a finding that Dabish and Kraut found in their CSW work that they had published recently. So I think we also need to look at social relationship, which we haven't done enough in this process.
Okay, thank you very much.
Thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.